Bismillahirrahmanirrahim. Today we are going to discuss how to name the optical isomers. You may have heard in a variety of ways the representation of the optical isomers. Most frequently we use the positive and negative notations for this. Sometimes we use small d and L for the representation of their optical rotation. Sometimes we use the capital D and capital L for the representation of their orientation, and sometimes we use the symbol R and S, like in this compound R2 chlorobutane and S2 chlorobutane, and even more than one chiral center can be represented by more number of R and S. So today we are going to see what does this means. First of all, let's begin with D and L conventions. The small d and L, which means dextrorotatory and levorotatory, and these names are most frequently represented by the symbols positive and negative notations enclosed in small brackets. Remember that the positive notation shows that a compound is rotating light in clockwise direction, or the compound is dextrorotatory and symbolized as small d, while the negative notation shows that it is rotating the plane of polarized light in anti-clockwise direction and is also designated as levorotatory or symbolized as small l. For example, here in this case you see the example of plus tartaric acid and negative tartaric acid. In past, the positive and negative signs were also replaced by the small d and L, but nowadays the signs plus and negative are frequently used for the representation of their rotation of plane of polarized light. Remember that the dextrorotatory or levorotatory nature of the compound is based totally on experimental facts. The experiments, if shows that the compound is dextrorotatory, it is represented by the plus sign and is called dextrorotatory, and if it is rotating, it is found to be rotating the polarized light in anti-clockwise direction, it is called levorotatory and is symbolized as small l. You can see that in this case both the isomers are mirror image of each other. Let them to enlarge up to a little extent. You see that this 3D model is the best representation of this diagram. which is the positive tartaric acid, and experiments reveals that this is dextrorotatory compound, so it is plus tartaric acid, while its isomer, which is negative tartaric acid, you can see it in two-dimensional diagrams, is levorotatory. This system is based on experimental facts. So from now you are clear that what does the plus and negative or dextrorotatory or levorotatory words means. Now come to another system which is most famous in carbohydrate conventions, the capital D and capital L conventions. This configuration was proposed by M. A. Rozanov in 1906, who told that the compound should be chosen as a reference, and the reference compound he chosen was glyceraldehyde. This is because he saw that changing in conditions may cause changing the rotation of the compound. So he observed that a standard should be there, which he proposed the glyceraldehyde because its relation with sugars and is the basic 3-carbon compound and the first member of the carbohydrate series and the most simplest one. You can see and compare the different isomers of glyceraldehyde which have different optical activity. Let them arrange as the two-dimensional diagram. You see that this is the functional group CHO, the second carbon which is the chiral carbon, and the third CH2OH group. Or with wedge and dash diagrams it can be represented by this way, and the three-dimensional model of this compound is like this. Both H and OH are projecting toward the viewer out of the screen. So let it arrange in the manner as in the two-dimensional diagram, while the negative glyceraldehyde, which is L-glyceraldehyde. Here you should remember that this negative and positive signs hold for their optical rotation, and capital D and L, they do not represent their optical rotation, but they show the orientation around the chiral center of the compound. The glyceraldehyde is a stranded. Remember, this is a stranded compound, and its plus isomer, which is dextrorotatory, is designated as D-glyceraldehyde. Remember, the word D is written in capital form here, and its levorotatory form is written as L, capital L, glyceraldehyde, and they have the orientation like this. You see the difference around chiral carbon atom. And you can see that they are not mirror images of each other. You see that in the 3D model, if they are arranged so that the hydroxyl group around carbon number 2 in the middle one stands for their mirror image. This rotation brings the compound in such a manner that they are mirror image at this point, but at the third carbon they are not seen as mirror image. Here OH is in front of the compound, and in this case the OH is projecting toward the behind side of the screen. So it seems that they are not the mirror image of each other in this case, but they are the optical isomers, as this compound is rotating the plane of polarized light in dextrorotatory direction, and this one rotates the plane of polarized light in levorotatory manner. Is levorotatory, of course. Now concentrate why they are designated as the positive D and the positive L representations. Remember that in the 2D diagram of the Fisher type, if the hydroxyl group in the carbohydrate series is written on the right side, it means that it is D series compound, and most frequently this carbon, which is a chiral carbon, in higher carbohydrates it is taken as the last one, last chiral carbon, which is farthest from the functional group. So in this case, this middle one is the chiral carbon, and if OH is written in the right side of the picture in Fisher projections, it means that it is D series compound. So this is D-glyceraldehyde, and if this OH is written on left side, it means that it is of L series compound and is called in this case L-glyceraldehyde. Remember, D and L both are written in capital form, and we have observed that the L-glyceraldehyde is levorotatory, so it is represented by the negative sign in bracket, and D-glyceraldehyde is dextrorotatory, so it is designated by the positive sign in bracket. But in many cases you will see that the D series compound could be levorotatory too. For example, the negative glyceric acid, which has the same configuration as positive glyceraldehyde, and actually the oxidation of plus glyceraldehyde with mercuric acid gives negative glyceric acid, which is levorotatory. But it has been found that the configuration around the chiral carbon atom remains same as of positive gracildehyde. So, although the compound is rotating the plane of polarized light in anti-clockwise direction and is levorotatory, but it is called D-glyceric acid. And you see that in this case where conversion of uh, glyceraldehyde is taking place into glyceric acid using mercury oxide. You see that the configuration around chiral center remains unchanged during the conversion, and a hydroxyl group is attached to carbon number 1 instead of the hydrogen. So the glyceric acid is formed, which has the structure like this, and the stereochemistry around the chiral center remains unchanged. This glyceric acid rotates the plane of polarized light in anti-clockwise direction, so it is designated as negative glyceric acid, although it has the same configuration as in positive glyceraldehyde, but the plane polarized light is rotated into anti-clockwise direction, so it is negative. Stereochemistry around the chiral center remains unchanged, so it is D series compound. You can see the stereochemistry is unchanged. So it does not mean always that the capital D series compound or capital D series compound are always dextrorotatory. They may be levorotatory. This shows that this system is a little bit ambiguous, and a single compound which shows D configuration becomes L in another systems sometimes. So the system is not used frequently, but is limited to chemistry of carbohydrates in understanding them, and of course it is most frequently used for the last asymmetric or the chiral center for the representation of stereochemistry of the uh, last chiral carbon. And if it is the hydroxyl group around them is at right side, it is of D series compound, capital D. And if the hydroxyl group is on left side, it is a uh, it is a L series compound. Remember, L here is written in capital form. Here, for example, we see some more examples of the carbohydrate series to understand the topic completely. You see that the D-glyceraldehyde, the OH is on the right side, and if this OH is on left side of the compound, it becomes L-glyceraldehyde. Similarly, the glucose, the very famous compound, when OH is on right side of the last asymmetric carbon. Remember that this is the carbon number 1 where the functional group is present, carbon number 2, carbon number 3, carbon number 4, carbon number 5 and carbon number 6. And of these 6 carbons, 4 are chiral or asymmetric carbon. This one is the first chiral carbon, this is the second chiral, this is the third one, and this is the last one and the fourth one. So this D and L convention represents the stereochemistry around this last asymmetric carbon atom. It doesn't has any relation with other chiral carbons. So if OH is on right side, it is of D series compound, and if OH is written on left side in Fischer diagram, it is the L-glucose, although both are enantiomers of each other. And same is the case of with other carbohydrates. For example, in fructose, this highlighted hydroxyl group at last asymmetric center is on right, so it is D fructose, and if this is on left side, this is L fructose. As you see that there are many asymmetric carbon in this 6 carbon hydrocarbon carbohydrate series. Different compounds have been written here and in D series. So there are also asymmetric carbons whose chemistry could vary, or the orientation around the asymmetric carbon is very essential to study. So the D and L convention is limited to last asymmetric carbon. It can't tell us about the stereochemistry of other carbon atoms which may different. So the D and L conventions do not works well in these cases. So a new system is needed for this. This new system is the R and S system of nomenclature, which provides very comprehensive results. And now we are going to discuss this system, which is very frequently used and very common in the naming of optical isomers. The R and S system of nomenclature provides a comprehensive naming of an optically active compound, and it describes completely the stereochemistry around the chiral carbons, each of the chiral carbons present in the compound. And so if there are 4 or more, even more chiral carbons, it can be represented satisfactorily and can be named with clear view using this system. In this connection, It has to be remembered that the direction in which an optically active molecule rotates the plane of polarized light is specific but is not related to the absolute orientation of the groups in that molecule around the chiral center. So, to assign an absolute configuration, following procedure is followed. There are different rules which are obeyed uh, to name a compound by this system. First of all, the chiral center is chosen and the group around it are examined and assigned their priorities according to their atomic numbers as by the Kahan-Ingold Prelog rules. So the different rules which are employed in naming the compound by R and S system, we use the following rules. The first rule is rank atoms directly attached to the alkene according to their atomic numbers. That is, we have to rank different atoms attached to the chiral centers according to their atomic numbers. The alkenes word was present in Kahan-Ingold Prelog, which is a duplicate here, but it is not necessary that the alkene is the case. Any of the chiral center in the compound is ranked according to their atomic number. The second rule is if there is a tie at any substituent, then look at the second, third, or fourth until a difference is found. There may be same atoms with the same atomic number. If such is the case, then for their priority, look for the second substituent attached to that carbon. For example, we will see this in naming the compounds. Number third rule is the multiple bonds count as multiples of that same atom. If there is a multiple bond, they will be counted multiples. Number fourth rule is rotate the lowest priority group to the back of the viewing angle and then draw a line, imaginary line, starting from the highest priority group towards the second priority groups. From the highest to the second priority groups, and from this line you will see that the line is in the direction of clockwise or anti-clockwise. If it is clockwise, the molecule is R. Remember, R is from Greek word rectus, which means right. And if it is anti-clockwise direction, then the compound is S. S from the Greek sinister, which means left side. For example, in this case, we have a compound where this is the chiral center of the molecule, the only chiral center in this molecule. Now we have to assign the ranking of the substituents attached to this carbon. You see that there is a hydrogen, a carbon, again a carbon, and a nitrogen. So we assign ranking according to their atomic numbers. The atomic number of hydrogen is 1, of carbon is 6, another carbon is 6, and for nitrogen the atomic number is 7. Here there are 2 carbon atoms. So we have to set priority for each of them. you see that this carbon contains furtherly 3 hydrogens, each having atomic number 1, and this carbon contains a double bonded oxygen. It is double bonded, so there are two different oxygen are taken for its representation, and another oxygen. So 8, 8 and 8. Thus this carbon, which has oxygen and 3 oxygens, one of them is double bonded, and 1, 2 plus 1, 3 oxygen, and this one has 3 hydrogens. So this carbon has more priority over this carbon. So now the nitrogen is most has atomic number greater all of these attached atoms, so it is in ranking stands first. The second is this carbon, and this one is the third in ranking, and this has the lowest ranking, which is the hydrogen. Now imagine that the lowest ranking is at the back of the molecule. So imagine a 3D model of the compound where the hydrogen is at the back. You see that this hydrogen attached with chiral carbon, I am turning the molecule in such a manner that it is behind of all in backward direction. And in two-dimensional diagrams, this can be done quite easily. You see that the hydrogen is turned represented by the dash diagram, which means that it is behind, and thus there remains 3 groups except for hydrogen, which is in backward direction. So now we have to assign priority. This is the nitrogen having most priority. Then this oxygen, which is for this carbon which is attached to the oxygens, double bonded with this one and single with this one, and the third priority goes to this carbon. This is the carbon. And in two-dimensional diagram, you see that this is the highest priority, this one the second in priority stands, and this stands in third priority. So if an imaginary line is drawn in your mind or on paper, you see that a line is there to represent the stereochemistry of the compound. This line is going from first priority to second priority, and from there to third priority. So we have to rotate this line in this direction. It means that it is projecting in anti-clockwise direction. This is an anti-clockwise direction. And if the compound is in anti-clockwise direction, its configuration is as S. So this compound is of S series, which means S means sinister or left towards the it means that S is in anti-clockwise direction, and if the line is in clockwise direction, It is represented by the symbol R. So this compound, which is this compound, which has the IUPAC name 2-amino propanoic acid, or this amino acid is also called alanine, and this isomer is of S series, which has this stereochemistry. So this is S-alanine. Now perform the same procedure with the following different molecule with different stereochemistry. Again, the molecule is alanine or 2-amino propanoic acid. But in this case, you see that when we put the lowest ranking hydrogen at the back side, this has the lowest in ranking, then again carbon and carbon. So this is nitrogen. Nitrogen has the highest priority. Second one is the carbon attached further with these oxygens, which gives him high in priority, and the third priority goes to this methyl group. So in this case, the first priority, second priority, and the third priority. And when the line is drawn from highest priority to the second priority group and then to the third priority group, the line is in clockwise direction. And we have seen that if the line is in clockwise direction, the compound is called R. So this is the R isomer of the alanine with this stereochemistry. This system is not only limited to single chiral carbon center, but it can be extended for the compound in which many of the chiral carbons are present. For example, here I have chosen an example which is 2-bromo 3-chloro-butane. We have two isomers of this compound. This is a diastereomer series. You see that one of them is the mirror image. Upper side of the compound is mirror image, but the lower side is not the mirror image, and such isomers are called diastereomers of each other. Here there are two chiral centers in this compound. One of the chiral is this one, and second one is this one, first and the second, and this one is the first and this one is the second chiral carbon of the compound. Total there are 4 carbons, of which 2 are chiral, each having different atoms attached to all 4 sides, which are chiral centers. So the stereochemistry of such compounds, in order to represent the stereochemistry, we take and extend the R and S system for each of the chiral carbon. This chiral is considered separately than this one. So there are two symbols S and R and R and R for these two chiral centers. 2 bromo, 3 chloro. So this is the carbon number 2. At carbon number 2, when you follow the rules, you see that now this is the carbon number 2. The lowest priority only concentrate on this carbon number 2 is hydrogen attached to this. Bromine has the highest priority, then carbon, then this carbon, but of these two this has the second priority because it contains a chlorine which has higher atomic number than the hydrogens. So next priority number 2 goes to this carbon which has a chlorine. So this is when you rotate the molecule hydrogen at back side, you see that the highest priority, then second highest priority, and this third highest. So imaginary line when draw in your mind uh, shows that this is moving in anti-clockwise direction, and anti-clockwise direction it is S. So 2S at carbon number 2, the stereochemistry is S. While in this case, when you move the hydrogen at backside, you see that highest priority, then the next second highest priority, and the third highest priority. The line is moving from uh, in an clockwise direction, so it is R. So this is compound is 2S and this compound is 2R. Now at carbon number 3, again you see that at carbon number 3, hydrogen, chlorine, carbon, and this carbon has the second priority because it contains a bromine. Turn the molecule in such a manner that hydrogen, which has the lowest priority, is at the back side, or same is the operation with this two-dimensional diagram. Hydrogen, imagine hydrogen in back side. The most highly uh, preference from this side to this carbon. The line is moving in clockwise direction, so it is R. And in this isomer, hydrogen is now at back side. This is the highly preferred. Then this one, this carbon has stands second in priority, and this one is third. Again, the line is moving in clockwise direction, so it is R. Clockwise direction is represented by the R. So both have same stereochemistry, so both have same R. Configuration. So this compound is 2S, 3R, and IUPAC name is 2-bromo 3-chlorobutane, and this compound is 2R, 3R, bromo 3-chlorobutane. But you see that as the number of chiral carbons increases, the complexity and the calculations also increases. So for compounds having greater chiral carbons, more calculations are needed for each of the chiral carbon. Hence, carbohydrates, which are the main um, and mostly studied compounds. They have four. In this series, there are four chiral carbons. 1, 2, 3, and 4. Now we have to calculate stereochemistry of each of the chiral center separately, which makes it somewhat difficult. Therefore, we use only the simplest system of naming, which was the previous one, the D and L system of notation, and is related to the last asymmetric or chiral center of the compound. Although this does not represent the stereochemistry very well, but is widely used due to its simplicity. The most recent and advanced system is of R and S system of the stereochemistry. Hope you have now understanding of this nomenclature system of the optical isomers. We will see the next topic in our next lecture. Thank you.